Could there really be a metal on Earth that's light enough to float on water? Lithium is the lightest metal on Earth, light enough to float on water, completely changing the way we think about metals. As the lightest metal of all, lithium possesses such unique physical and chemical properties that it's become an indispensable material in modern society. What makes lithium even more fascinating is that it's used in fields completely different from the traditional roles of metals. In some ways, it almost doesn't feel like a metal at all. So today on Dr. Saivira, we're going to explore lithium, the lightest metal on Earth. Let's dive right in. Lithium is considered one of the earliest elements formed after the Big Bang. But billions of years later, humans on Earth had no idea it even existed. So how was lithium first discovered, and where did its name come from? It all started with a mineral called petalite. Petalite was first mined in the late 18th century on the island of Uto in Sweden. At the time, it was an extremely rare mineral that hadn't been found anywhere else in the world. Naturally, scientists couldn't help but wonder what this mysterious mineral actually was. Then, in the early 19th century, Swedish chemist Johan August Arfwedson began studying petalite and realized it contained a type of alkali metal distinct from the already known elements sodium and potassium. By the way, the word alkali comes from the Arabic word alkali, which originally referred to substances that neutralize acids. In other words, bases. That's because alkali metals react with water to produce hydrogen gas and hydroxides, forming highly alkaline solutions. Getting back to the story, Arfwedson named this newly discovered alkali metal lithium. Interestingly, the name comes from the Greek word lithos, meaning stone. So why would a chemist give a metal a name that literally means stone? Well, the reason was quite simple. At the time, other known alkali metals like sodium were extracted from seawater, salt flats, or seaweed, while potassium was obtained from plant ash. In other words, people didn't expect alkali metals to come from rocks or minerals at all. Lithium, however, was the very first alkali metal discovered in minerals, in other words, from stone itself. In fact, considering how many elements are discovered in minerals, it almost feels like some element was bound to end up with the name lithium eventually. Kind of makes sense, doesn't it? After Arfwedson's discovery, several scientists succeeded in isolating lithium in its pure form. However, it couldn't be produced in meaningful quantities until 1855, when Robert Bunsen and Augustus Matthiessen developed a process to extract lithium through the electrolysis of lithium chloride. And interestingly enough, the fundamental principle behind that process remains in use even to this day. The Robert Bunsen I just mentioned is actually a scientist I talked about in my previous episode about Mendeleev. In fact, Dmitri Mendeleev, the legendary chemist known as the father of the periodic table, studied under him during his years in Germany. And beyond developing large-scale lithium production methods, Bunsen made numerous scientific contributions, including the discovery of rubidium and cesium, as well as major advances in spectroscopy. So if you're interested, he's definitely someone worth looking into. Anyway, that leads to an interesting question. Is lithium still mainly extracted from rocks today? Well, this is where the story gets really interesting. Take a look at this table showing the world's largest lithium reserves. But the really important thing here isn't just how much lithium these countries have, it's the form that lithium exists in. While Australia primarily mines lithium from hard rock, South American countries like Chile and Argentina hold vast amounts of lithium in highly concentrated brine beneath salt flats. In fact, these brines are considered one of the most important lithium resources in the world today. So then, what exactly are these salt flats? Simply put, a salt flat is a vast area covered with salt left behind after ancient lakes evaporated away. These environments are usually found in extremely dry regions such as deserts or high plateaus. Beneath the surface lies mineral-rich underground brine, and over long periods of time, intense evaporation concentrates those minerals even further. When large amounts of lithium are dissolved in that brine, it's known as lithium brine. And interestingly, the extraction process is surprisingly similar to how sea salt is produced. First, underground brine is pumped to the surface and stored in massive evaporation ponds. Then, over the course of several months, sometimes even up to a year, the water is slowly evaporated using sunlight, gradually increasing the lithium concentration. Once the brine becomes concentrated enough, lithium can finally be extracted from it. Today, these lithium-rich brines are considered one of the world's most important lithium resources. Of course, large amounts of lithium are still produced from hard rock and clay deposits, but even today, lithium extracted from brine accounts for a significant portion of the global supply. And when you think about it, it's actually pretty ironic. The name lithium comes from the Greek word for stone, but if the element had been discovered a little later, after we began extracting large amounts of it from salt flats, we might have ended up calling it something related to salt instead. Now that we've covered where lithium comes from, it's finally time to take a closer look at the unique physical and chemical properties of lithium. Lithium's chemical symbol is Li and its atomic number is 3. As the lightest of all metals, it occupies a unique place on the periodic table. With a density of just 0.534 grams per cubic centimeter, lithium is less than 1/3 as dense as beryllium, the second lightest metal. To put that into perspective, lithium is so light that its density is only about half that of water, making it one of the few metals capable of floating on water. And true to its reputation as the lightest metal, its melting point is also relatively low, at around 180 degrees Celsius. Like most metals, lithium has a silvery white metallic luster. It's also relatively soft and ductile, so soft in fact that you could easily cut through it with a regular kitchen knife. However, lithium is also highly reactive. It reacts readily with oxygen and moisture, so if it's left exposed to air, it begins to oxidize almost immediately. So where is lithium actually used today? By far, lithium's largest application is in rechargeable batteries. You've all heard of lithium-ion batteries before, right? Today, lithium-based rechargeable batteries are essential energy storage systems used in smartphones, laptops, and electric vehicles. But do you know who first brought lithium-ion batteries to the mass market? It was Sony back in 1991. Sony eventually began equipping many of its iconic products with lithium-ion batteries, from portable video cameras and cassette players to the Vaio laptop series. At the time, one of the biggest showcases of Sony's portable technology was an ultra-compact laptop designed to fit into a back pocket. Well, technically only part of it actually fit into the pocket, which naturally led to plenty of jokes and parodies, but back then it was still considered an incredibly impressive piece of technology. Today, most of those electronic devices have faded into nostalgia, but there's no denying that many of the hit products that helped define Sony became even more advanced after adopting lithium-ion batteries. So then, why is lithium so well suited for rechargeable batteries? To understand why, we first need to talk a little about batteries, but since this episode is all about lithium, I'll keep this part brief. The qualities of a good battery are actually pretty straightforward. First, it needs to deliver electricity efficiently, and since electricity is essentially the flow of electrons, a battery needs to be able to release electrons easily. Second, it needs enough capacity to supply those electrons over a long period of time. Third, for portability, it has to be lightweight. And finally, faster charging times make a battery far more practical for everyday use. And interestingly enough, lithium turns out to satisfy all of those requirements almost perfectly. Among all metals, lithium has an exceptionally strong tendency to lose an electron and become a lithium 1+ ion. In other words, lithium gives up electrons very easily, making it one of the most electrochemically reactive metals. At the same time, it also readily participates in reduction reactions involving electron transfer, and that's exactly what makes lithium so effective for both charging and discharging. Because of these properties, lithium ions can shuttle back and forth between the cathode and anode very efficiently, allowing electrical energy to be stored and released effectively. Lithium-ion batteries also make very high-capacity battery designs possible, and this comes down to two things: lithium's tiny atomic radius and its low atomic mass. Because lithium atoms are so small and lightweight, a much larger amount of lithium can be packed into the same battery volume. This allows for much higher energy density while also reducing the overall battery weight. And during charging and discharging, lithium ions move between the cathode and the anode. Since lithium ions are among the smallest and lightest metal ions, they can move very quickly. That makes lithium a highly effective material for improving charging speed and optimizing battery performance. When you take a step back and look at the bigger picture, lithium almost feels like a material perfectly suited for one of humanity's greatest engineering achievements, the battery. Of course, no material comes without drawbacks. To maximize driving range and performance, electric vehicles rely on high-density battery systems such as nickel-cobalt-manganese or NCM and nickel-cobalt-aluminum or NCA battery systems, which can store large amounts of lithium ions in the cathode. However, this high energy density also comes with a greater risk of fire or explosion. To solve this problem, researchers are developing various thermal runaway prevention and battery protection technologies. At the same time, alternative systems such as lithium iron phosphate or LFP batteries, as well as all solid-state batteries designed to replace liquid electrolytes, are also being actively developed. But is lithium used only in batteries? Of course not. And the next application of lithium is probably something most people would never expect. In the medical field, lithium is used in the form of lithium carbonate as one of the most established treatments for bipolar disorder, also known as manic depression. This condition involves recurring cycles of mania, where emotions become abnormally elevated, and depression, where people experience severe depression. During manic episodes, symptoms can include unusually high energy, impulsive behavior, and insomnia. During depressive episodes, people may experience extreme sadness, lethargy, and even suicidal thoughts. And interestingly enough, lithium plays a very important role in treating these symptoms. Lithium helps regulate several neurotransmitters involved in signal transmission between neurons in the brain. In particular, it's known to help regulate neurotransmitter activity, including glutamate, one of the brain's primary excitatory neurotransmitters, while also helping stabilize neural signaling. Because of this, lithium is known to help control manic episodes and reduce extreme emotional swings. And beyond medicine, lithium is also used in the aerospace industry to produce specialized aluminum-lithium alloys that are both lightweight and high strength. On top of that, lithium is also being discussed as a key material for blankets used in future nuclear fusion reactors, such as tokamaks, where it could be used to breed tritium fuel. So today we explored lithium, the only metal capable of floating on water. Thanks to its exceptional energy storage capabilities, lithium has become one of the key materials behind modern battery technology. But as we've seen today, lithium's applications extend far beyond electronics. It even plays an important role in medicine by helping regulate neurotransmitters. And as electric vehicles and renewable energy storage systems continue to grow, the importance of lithium will only continue to rise. At the same time, lithium is still a finite resource with limited reserves, which means technologies for efficient lithium use, recycling, and next-generation battery materials will likely become even more important in the future. If you enjoyed today's deep dive into lithium, please don't forget to like, subscribe, and turn on notifications. I'll be back again soon with another fascinating science story. Thanks for watching. This has been Dr. Sai Vera.